The lecture 4 is about the unit operation model in process design. In a chemical process design, we needed to define the model for individual equipment. Then we combine the number of the unit operation model in order to complete the modeling of the overall process. So we are looking at how we can model for equipment by equipment in these lectures. So we needed to setting up the unit operation model by having probably mass balance and the energy balance. So you're probably familiar with the mass balance and the energy balance. So for example, conservation of the mass is given by the total mass out will be given by total mass in minus accumulation of the mass. For individual component I, for example, in the reactor, the mass out will be summation of the mass in, generation, then minus consumption, and minus accumulations. So you will have seen a lot of the example for the conservation of the energy by taking overall energy used in the process will be given by energy out equal to energy in minus accumulation of the energy. So the first step of unit operation modeling is to take the mass balance and the energy balance and quantify input against output. Okay, there might be accumulation, there might be generation, there might be some consumption of the particular component. And we want to relate between input and output in terms of the mass, then we have to use the mass balance. Between the input and the output, then we want to set up the energy flow, then that should be quantified by the energy balance, okay? So let's say this is CSTR. So there is an input F SA J0. Then there is the outgoing stream that is given by Fj. What is the mass balance for this component? So the out minus in minus out. Then we have the generation or consumption. Then the remaining term will be accumulation. So accumulation will be given by number of moles of the particular component J against time will be quantified the mass balance. So input and the output, how they quantify in the reactor system design for the generation or consumption of the reaction, that will be quantified by this expression. Against the volume, then with the kinetics, then we have the accumulation integration for the reaction rate over the volume. Then we can calculate how much the component is generated or consumed inside the reaction, okay? So this is the example of the mass balance. Then how do you use this mass balance, okay? So we quantify between input and output and other things. Then using this, we can further developing for some the equation for having some information, like what is the information you need for having the CSTR. For example, I want to calculate the volume. I want to calculate the volume of this reactor. How can I calculate it? So from that equations, this generation term, okay? Based on this, we have the simplified expression as V equal F for CSTR case, okay? So because in a steady state, we may assume this term to be 0, okay? Then that is not the compressible the fluid, then we can take this one as the minus, Rj and V plus Rj plus V. Then we have this relationship for CSTR at the steady state. Okay, sorry, steady state. So at the steady state, volume can be calculated from this mass balance. Okay. How do you consider reaction kinetics? That will be quantified by the specifying the particular reaction kinetics. Let's say Kca square. So maybe reaction is based on the second order. Maybe Kca, whatever. Okay, and Cb square, whatever. So based on the kinetics, we can quantify some of the rate of the reaction for evaluating of the volume. Okay, so we get this expression based on the by setting up the mass balance. So how do we calculate the Q required by this CSTR? Maybe this reaction, maybe endothermic, maybe exothermic. Let's say this reaction is exothermic. Then we have to take out the heat. So how can we take out the heat from the CSTR? We might have the piping. Then the cooling water is circulated. Then we can take out, let's say, heat. Okay. So how much cooling water is required? Then we can calculate Q based on what? We need to set up energy balance. Based on the energy balance, then we can estimate Q, amount of heat to be removed by this process. Then we can estimate the flow rate required by cooling water. Okay. So the everything typically in a chemical process design starts from mass balance or energy balance. By using this expression, adding more fundamental the knowledge or some the practical information, whatever you call, and adding some knowledge into this mass balance and the energy balance, and getting some more information. For this case, I can estimate the volume required by the CSTR. From this energy balance, I can estimate how much cooling water is required to take out the heat from this CSTR. So energy balance and mass balance are the kind of a key equation in a mathematical expression to start the modeling of the unit operation. Okay. Now we can check the unit operation modeling for assessing a feasibility of a proposed the process. Okay. So we can check the temperature and the pressure and the purity, phase change, phase separation, etc. Then check whether the condition you set or the operation procedure you set in the design is economic or is practical or is feasible. Okay. So you have a design, say, then you need to check the feasibility of the process. Okay. So this is a reactor. So let's say this reactor is PFR. The volume required by this reactor is, let's say, 10 cubic meter. Then you can set up the mass balance, then calculate the volume. Okay. Then, but based on the volume you have, then your suggestion by taking 10 cubic meter can be compared. Then you can say whether your suggested the size of the reactor is feasible in terms of the calculation you have from, let's say, mass balance. Okay. So you might have done, let's say, the reactions. So in the reactions, let's say A to B, I want to have the conversion 90%. Okay. as long as I increase the volume of the reactor, I may be able to achieve 90%. But what about these equilibrium reactions? So this equilibrium reaction is governed by equilibrium condition, okay? So can I get the 90%? Sometimes yes, sometimes no, because that is governed by equilibrium. How do you check? We needed to check the equilibrium reaction kinetics, then see whether we can achieve this equilibrium conversion, okay? In the working sessions 3.2, we needed to find out the temperature in a condensation. So in that example, we needed to cool down the air down to a particular temperature in order to have condensations, okay? Now we can use the unit modeling by taking thermodynamic estimation for this calculation based on the composition of the Y, okay? So then if you want to check whether you have the proper contaminant level for the cooling gas, then through the thermodynamics, then I can check the temperature T prime, then I can see whether I can achieve this specified contamination level for the cooling gas. How do you do it? Based on the thermodynamic equation. So this is model for condensation, model for cooling, okay? So we can use the unit operation modeling for checking the feasibility of the proposed process, okay? Then we can determine size of the equipment, that is called the sizing. Then sometimes we want to check capacity of the existing equipment, that is called rating. So let's say we have the heat exchangers. So the simple one is, say, fluid A goes into that direction, and fluid B goes into that direction. So heat is transferred, then we want to find out the Q between the stream A and stream B. Then I explained that such that Q will be estimated with over heat transfer coefficient U and the heat exchange area and log mean temperature between these four temperatures, okay? In, out, and T in, T out, stop, okay? So based on these four temperatures, we can calculate the log mean temperature difference. Then based on the physical property, we can assume the overheat transfer coefficient. Then the sizing means based on Q and temperature, we can estimate A, okay? Based on the amount of Q to be treated by this process, then based on the temperature given, we want to estimate A, that is sizing. We want to check the size of the unit, okay? So how do you calculate this Q? For example, based on the amount of Q for this CSTR, then I can estimate the amount of Q from energy balance, okay? Then based on the energy balance, okay, and based on temperature we have, we want to check we want to check the size of the heat exchanger required by this process design. This is called sizing. What about the rating? This is for the new design. We want to find out the size required by this process for new design. For rating is typically for existing plant. We have the based on temperature and A, we want to estimate Q. Based on T means that this is temperature is operating conditions. Okay? A is given because we are looking at existing plant. Okay? So you have the certain heat exchanger given. Then you want to check whether we have enough heat transfer, enough heat exchange. That will be checked by based on A and based on T. That is called rating. We checking existing unit whether we achieve the heat transfer we want. That is rating. Sizing is different. This is target. This is amount of Q to be treated by the process. Then how much heat exchange area is required. How big, how small. Heat exchanger should be brought into the process. That is question of sizing. So that is the typical activity for the new design. The rating, that is typical activity for existing plan. If this is not enough, then we need additional heat exchanger. Okay? If this is not enough, heat is not transferred properly, in order to increase the performance of a process, then we need to add new heat, okay, heat exchanger for the process. How do we check it? Using the model. Okay, so that's why modeling is important in a chemical process design. So material energy balance explained. Then we need to understand the governing principle. What is the governing principle? Governing principle is kind of the mathematical expression for your modeling. It can be this equation. This can be that kind of equation, that equation. These things are called as governing principle, okay? Now we needed to identify problem input. What is the input for the sizing of this heat exchanger? I have to specify Q. I have to specify temperature. I needed to assume U. Otherwise, we cannot calculate A. Okay? So we needed to identify input based on the input. Sometimes it's given, sometimes assumed, sometimes provided by the external company. Then we can calculate something. So identify the problem input. Then we needed to identify further whether we need additional input required to solve the problem. So for example, x, ey equal to 5. X is given. Okay. Then can I get the y? Yes. Because x1 is given, then I have the y. So it's a problem solved. X1 is given. Can I solve? Yes, I can solve the y. Although we have two equations, then the degree of freedom is 1. So x1 is given, then we can solve that equation. However, if x1 is given, then we have different solutions, right? So that is over specified. Okay? So we don't need to give that because we have two equations, two degree of freedom, two equations, and we have to find out two variables x and y. So we can solve without specifying any number. Okay? So this is given, that is given by user or assume. So that is the so-called specifications in the process modeling. So if this is given, or this is given, or this is specified, then that is additional input in order to calculate A. Okay? So we needed to provide the input If not enough, then we have to give additional input. Okay? So design can then be done through the sensitivity study by varying input. Okay? Say in that heat exchanger, we have Q, U, A, delta T, log mean temperature. So in a heat exchanger, one is T1 and T2. That will be T3, maybe T4. So we can calculate the log mean temperature here using 4 temperature, okay? So this is TA. Let's say this is TB. Then the TA minus TB and log TA minus TB. This is TB, okay? So based on the 4 temperature, we have the log mean temperature, okay? So let's say Q is given as a 1 megawatt. Then U is assumed, let's say 1,000, whatever, okay? What is A? I can calculate A based on Q, U, delta T, log mean temperature, okay? I can calculate the heat exchanger area based on this assumption. Then overheat transfer coefficient is assumed to be, let's say, 1,000, maybe 100, but I'm not sure whether this is correct or not. Let's say I take 100 based on this fluid A and fluid B. Then this might be correct, but I'm not so sure. Then what I can do is say, what if U is 100? What if U is 90? What if U is 80? So we can change the value in order to have the number or calculated one from your model, okay? So this is the sensitivity analysis. This called sensitivity study by varying input, okay? Once we have a model, then you can see that the relationship of the sensitivity by changing certain input, okay? So this is the example, very simple example for the unit operation. We do not consider any the energy balance or any separation related with the modeling. We just set up the model based on the mass balance. So 2 components are assumed to be fed to this simple separator. So one is A and the other one is B. The input is given as F, and the top product is given as D, and the bottom product is given as B. The mass balance is given as F equal to D and B. Then we have the A component, B component for the feed, as well as D component, top product and the bottom product. So we can set up the material balance for the A and also B, okay? So we have 3 material balance. Now we have summation equation. When you're adding up these 2, it must be 1. When you're adding up these 2, it must be 1 because the x is mole fraction. Okay, so we have 3 summation equations. We can define the recovery. Recovery is given by R for A in terms of the top product of D. So the dxAD divided by xAF. So we have the product recovery defined by this expression. So based on the amount of the A produced in the D against the amount of the A fed to the column can be used to calculate the product recovery, okay? Then we can specify the other things in this model. So flow rate, input flow rate is given by 1,000. D might be given as the 500. Then XAF might be given as 50%. Then the top product is A component composition specified as the 99%. The recovery is set as the 98%, okay? So 5 specifications are given as an input. Then when you're looking at the number of the variables here, then we can have the 10 variables, okay? So F, D, and B, these are 3 flow rate, and the 6, the composition for each F, D, and B flow rate. Then the recovery of the product is given by R. So we have 10 variables to be determined by this expression, and then we have the overall 12 equations. So 3 material balance and 3 summation equation, 1 product recovery, and 5 input. We have the 12th equation, but if you're looking at the equation carefully, by having these 6 equations, we can have the additional non-independent equation. Let's say if I using these 5 equations, I can have this 6 equations, okay? When I having these 5, then I can have the additional 1. So the not all 6 equations are independent. So one equation must be dropped. Let's say example 1. So the 5 equations are independent. One equation is dependent. So we need to take up one equation out. So we have the 10 variables. 10 variables. Then the number of equation is 12, but we have to take a 1 out. So number of equation is the 11. We have the 10 variables. The number of equations available from our modeling are 11. So we have the 1 short of the degree of freedom. So we have to specify one more thing. So we have to specify either D or XAD or RAD. So this must be taken out from the specifications, okay? Sorry, we're not adding it. We are taking out because the number of equation is 1 more than the number of variables, okay? So we have more than the enough for solving this problem. So one of these 3 might be taken out, okay? That is up to the decision by you. So I may taking out D from the problem specification. The number of variable is the 10 and the number of equation is 10. So we can solve the problem, okay? So in this simple example, we have 2 components involved in this separation. So based on the product recovery and with some the initial information given in the beginning, then we can solve this problem, okay? But as I said at the beginning, we did not consider energy balance and any equation related with thermodynamics. So the actual distillation modeling is very complex. Anyway, that will be discussed in the lecture 6, okay? So we're looking at this simple example as an illustration how the model can be set up and how model can be relaxed, or how we needed to add more input in order to complete the unit operation model, okay? So based on the number of equation and number of variables, then we may add more input to the process. For this case, we needed to take out one of the equation in order to have the 0 degree of freedom, okay?